Hello, everybody. In recent months, I've received many questions related to time series modeling with copulas. So in this video, we'll take a look at univariate time series modeling, which is time series, single time series. So that's where the univariate comes from. And in a future video, I'll also discuss multivariate time series modeling. So the general framework, so the structure of this mini lesson today is going to be, we're going to talk about the general framework for univariate time series modeling. And then we'll walk through a synthetic example where we generate some data and show why copula modeling can be useful. And finally, we'll do this with a real live data set as an example, so that we can show the practicality of this method. So let's start with the framework, and a lot of this builds on all of the content that we've gone through in previous lectures, so please refer to that as needed. But with that, let's begin. So let's start with the framework for univariate time series modeling. So suppose we have a series of observations, so we can call this a signal, and this signal is represented with in this notation as x of t plus 1, and so forth. So at a given time, we make some measurement. That measurement can be of anything. It can be measuring the price of a stock. It can be measuring the temperature at a given location, and so forth. And so we do this, and we do this at a given set of times, and from that we have a time series signal. So that's what this first equation represents, is a time series. So from this time series, let's move this into the copula world. So the way we're going to do that is we're going to do it in two steps. The first step is that this is not something I'm doing special. This is time series modeling literature. This is standard stuff in time series modeling, where each value, so each observation at a given time, so in this case x of t, is a distribution. It follows some distribution. Now this can be, so if a time series can be a deterministic signal where we generate a signal, let's just say it's like a flat line or an increasing line or decreasing or a sinusoidal wave, or it can be something random, which is more likely what occurs in nature, where we have some fluctuating measurement like the temperature. It follows some pattern, but everyday measurements are going to vary slightly. So what we can do is we can model each observation as a probability distribution. That's what this equation is showing here. Xi follows some distribution f of x. So okay, so we've done the first part of the modeling where we're saying that each measurement is a distribution. Now we can create a joint distribution out of this, and we can do, this is flexible based on your application, but one way to do this is we can say, okay, if each point is a distribution, then what is the joint distribution between a measurement at time t and the measurement at time t plus 1? And that's what this is showing here. So for any given signal with hundreds of data points, we can take every pair of values, sequential pair of values, and note that this lag in this case is 1, but it doesn't have to be 1. It can be anything you want it to be based on your particular application. But I'm just showing an example here where we're saying, let's take a look at the measurement at time t. Let's take a look at the measurement at time t plus 1. Because they're both now being modeled as distributions, then that means that there exists some joint distribution between them. And that can be modeled by a copula, CUV, for all time t. Now, if there is no relationship, it can be the independence copula, which we've discussed previously, or more likely in some real life time series measurements, there will be some distribution by which they are related, although that distribution is probably unknown, and maybe not only unknown, maybe it's also a weakly dependent distribution. That being said, you can model this with this general framework. So this is these three equations represent our general framework for univariate time series modeling. Okay, so given this, now that we've established this framework, let's go through a couple of quick synthetic data examples to show how this can be used. And remember that after these synthetic data examples, we'll go through a real life example. So to start with, we have some code here, and this is code that we've used previously, which generates copula observations from different copulas. So in this case, I have a function to generate samples from a Gaussian copula, a Clayton copula, and a Gumbel copula. And then what I'm going to do is I have this function called generate time series, which generates a time series given a particular copula type and the parameter of that copula. And remember that the copula generates the samples that give you the dependent structure between them, but we have to apply some marginal distribution so that we can actually create like an observed signal. So what we'll do, just to demonstrate the difference, like the point of this lecture is to show the power of the dependence modeling. So we'll keep for every signal that we generate, we'll generate it such that the individual measurements all come from a normal distribution, but we'll apply different dependent structures and see how that affects the generated time series. So that's what this function does. And remember, all of this code is open source. You can go online and take a look at it. And feel free to drop in any questions or either on YouTube or even on the GitHub page, and I'll do my best to answer them. So that's why I won't go into the code in detail here, but we generate these time series where we choose the copula type, we generate the samples from the copula, and then we apply the marginal distribution to it. So in this case, I'm going to generate 1,000 data points of time series with different copula types and different parameters. And then given this, I'm going to show some ways to look at this data. So the first way, like a typical way we might see a time series is a signal like this, where we just see some randomly fluctuating points. And it's actually very hard to see what's going on in this. So I just showed this because this is what you might be used to, but these plots really don't tell us much. Like given these plots, it's pretty much impossible to say, oh, this came from a Gaussian copula and this came from a Clayton copula and so forth. Like it just looks like random points, right? And so remember, so let's look at a lag plot. And the lag plot, what it will do is remember that the way that we generated the data was that we said that there is a relationship given by the copula that we generated between a particular time and the next time. So a lag plot, what we will plot in these lag plots is we will plot x of t on the x-axis and x of t plus 1, which is the next time, on the y-axis. And we will look at the relationship between the points for these two times. And so when we look at these plots for the data that we generated, this is data that we generated with a Gaussian copula, a Clayton copula, and a Gumbel copula. And now you can start to see there's some interesting differences between them. So remember that the Gaussian copula models linear dependent structure. So what we see here between consecutive samples is a correlated data set that comes from a joint normal distribution, because remember that the marginals that we generated were also normal, and we generated it with a correlation coefficient of 0.7. So we see a slight oval that represents that correlation coefficient. And if we look at the consecutive samples of the Clayton copula, we see a very interesting dependent structure. Here we see what's called a negative tail dependence. And in this negative tail dependence, what that means is that if you see when two values are high, there's less of a correlation between them because the scatter plot's very spread out, but it gets tighter when the data are both negative or small relative to the large ones. And this is what this Clayton copula models, is it models this sort of negative tail dependent structure. And the Gumbel copula, it models a different kind of dependent structure. You can see that here. So so what did we do here? Let's just recap. What we did was we created time series with different dependent structures between consecutive samples. We plotted them. We showed that looking at the raw time series, there's not much to see. But when we look at the lag plots, we can see that there's a clear dependent structure. And that is what we would expect because we synthetically generated the data this way. Okay, so the point of this was to say we can generate data and there's a way to look at it with Copulas. So why is this useful? Let's take a look at a concrete example where we can use this sort of time series modeling. So let's do this. So what we're going to do in this notebook, I'll skip this and you're welcome to look at it. But this is just another way to look, these heat maps are just another way to look at this, these scatter plots. So let's look at a practical example. What we're going to do is we're going to try to do some modeling of temperature data. And in this notebook, what we have is we're going to download temperature data from a location in California called China Lake. And this is the coordinates of China Lake. China Lake is an area in the desert that gets extremely hot. So why this might be interesting to model for Copulas is that these temperatures are sort of sticky. Like if it's hot one day, it might be hot the next day. So thinking along these lines, like we might be interested to know if my temperature is a particular value today, what is the distribution of my temperature tomorrow? And does this data set have this sort of relationship that's worth modeling? So let's take a look. So our first step is to download this data. So we're going to use this package called Medio. Let me look at the full package name, Mediostat. So Mediostat is a very cool package that aggregates weather data or temperature data and probably others that I haven't really explored. You give it a lat long, you can download some data for it. And here I'm going to look at the maximum temperatures to see how sticky these max temperatures are. So I get this data set for 2 years for China Lake. And here's a plot of this time series, right? So it shows, this is showing some seasonal trends, right? Like in July, the heat, the height of summer, you have very high temperatures, and this happens cyclically. So this is interesting. So is this useful for Copula modeling? So let's do some, let's look at this from more exploratory data analysis perspective. So we can also, remember that previously we modeled, and what I said we were wanting to model was, if we know the temperature on a particular day, what is the temperature on the next day? So we're going to look at this data. This call to interpolate just fills in data that might be missing. It doesn't really mess up our analysis in any way. Although you want to be careful with this sort of thing when you're working with real data. But that being said, this is just a way to kind of smooth out the data. And then this indexing is basically me looking at the relationship between the temperature on a given day and the temperature the next day. And what this scatter plot is showing is that there is a pretty strong relationship between the two. Like if we were to do a linear regression, we could fit a line and predict, given a particular day, what is the next day's temperature going to be, with a pretty good confidence. But the linear regression won't give you a probability distribution. That's where a Copula can give you a probability distribution. So this is what the scatter plot looks like. And this is some code which is going to compute a couple of metrics to see what this data looks like from a quantitative perspective. Like qualitatively, we can see that there's some strong relationship. What do the numbers say? Well, the numbers say that there's a very, very strong relationship between the two. So the Pearson correlation and the Kendall's tau are both very, very strong, whereas the tail dependence metrics are not super strong. So there's not a very strong tail dependence, but there is a very strong overall dependence between the two. So let's try to model this. So let's try to model this with Copulas, right? And what we have here is a bunch of code that fits various different Copulas to the data. And there was a previous lecture on how to fit Copulas to the data, so I won't go through those details again, but that's what this does. This fits a bunch of different Copulas to the data, And then what we can do is we can fit the data, which basically finds the parameter that models the data the best. And once we fit the data, what we can do is we can generate synthetic data from that copula and then visually first inspect whether that copula is modeling the data well. And so here's a plot which shows the original data, which is shown in black, the true data, and then the blue shows synthetic data that's generated from the copula. And we can see that visually, the Gaussian, Gumbel, and Frank copulas all seem to fit the data pretty well. The Clayton copula is modeling some strong tail dependence here, so it does not fit the data well at all. But we can do this more quantitatively. And to do that, we can use a goodness of fit test between the copula and the data. So here I'm using a Cramer-von Mises statistic. And in this statistic, the lower the value, the better. And what we see is that the Frank copula is the best fitting. Here, lower values are better. So we see Frank, and we see the parameter of the Frank copula is 24. So, okay, great. So we fit a copula between the data at time t and the data at time t plus 1, the temperatures. And now what do we want to do? We said that our goal was, if we know the temperature at time t, what will the temperature be at time t plus 1? And what that means is that what we're really asking for is to compute a conditional distribution. And a conditional distribution, what it is to say, given the more precisely, given the temperature at a particular time t, what is the distribution of temperature at time t plus 1? And to compute this is not a trivial calculation, but luckily there's a very cool package called pycopuvinelib, which is a port of an R package that does this. And this package allows you to do this inference problem. So this is an inference problem. It's saying, given a particular value, what is my distribution of the other dimension? And so I have this function which does this for various copulas, and we can see the results. So you're welcome to go through this code, but I've created a visualization that shows what this looks like, how this manifests. So for these different copula configurations, given a particular time, we can see, if I change the slider, how these distributions change. So what this inference allows us to do, it says, okay, my temperature is 33 degrees, and I've modeled the dependence between the temperature time t and time t plus 1 with these different copulas. Then what is my forecast of the temperature at time t plus 1? So let me go through this in a more concrete way. If my current temperature is 33.5 centigrade, and I've modeled this data with a Gaussian copula, then the maximum, the value which has the highest probability that the temperature will be tomorrow is actually, it seems to be around 33.5. It's the same value. Whereas if I modeled it with the Clayton copula, you can see that the highest probability is somewhere in the 40s actually. And with a different copula, it's a different value and so forth. And so when we do probability distributions, the point is not to look at point values. I was just showing that to kind of point out the differences. But this is how we might use the time series modeling, where we say, okay, given a particular value, what is the distribution of values on the next day? And so this is a slider widget that we can use, and you can explore how different copulas are modeling this temperature data. And that wraps up our introduction to univariate time series modeling. So as always, feel free to leave questions in the comments below, and I'll try to address them in future videos. Please subscribe to my channel, and thanks for watching. In the next video, I'll extend these concepts to multivariate time series, where we'll need to consider not just temporal dependence, like the dependence between samples, but also cross-sectional dependence between different time series. And thanks again. Talk to you guys soon.